In this next section, we're going to consider Descartes' rule of signs and factor bounds. These are going to be tools and techniques that let us look at a polynomial and really get down to a sort of theoretical understanding of what it does and what it's going to do. We understand this section well, and that's going to take a little bit of time and practice, but if we understand this section well, then we're going to be able to quickly and easily understand if calculators are correctly factoring for us. Technology sometimes has difficulty with that kind of stuff. We're also able to know some understanding about what the graph or the curve of these functions might look like. So let's start out with the fundamental theorem of algebra. It just promises us that if the degree of the polynomial is bigger than 0, then there has to be a root somewhere that will make this guy be equal to 0. So all the fundamental theorem of algebra is saying is, provided our polynomial has a degree bigger than 0, we have a root. Then the factorization theorem goes a little bit further. It says, look, if n is a positive integer, and if the degree of our polynomial is n, and I think just about everyone coming out of an American high school knows this, then we're going to have n answers. And in particular, we now know if we have n answers, that means I can factor it into n pieces, n straight line equations. We may have some of those equations show up more than once because we're thinking about multiplicity. That's okay. When we factor it into these pieces, in particular, these straight line pieces we go into, we're going to have different roots. The zeros we've been talking about, R1, R2. If we want to talk about all of them, we call that Ri. And this notation right here simply says that our roots are going to live inside the complex numbers. Remember, the complex numbers are the ones that look like a plus bi. Real numbers are inside of the complex numbers. But we're saying, look, our integers, our numbers, excuse me, not integers, our numbers, our coefficients in front of the x's are going to be inside the complex number place. In particular, we have something else. If we know that these coefficients in front of x, in fact, aren't just any complex numbers, but are rather the real numbers, then, and that's what this says, if those coefficients are inside the real number line, then we know that if I happen to have a complex number as a root, now notice the distinction. If my coefficients are real numbers, and if I have one complex number as a root, then I know that I'm going to have its complex conjugate as a root as well. So what this says, this theorem right here is saying, is that if I have coefficients that are real numbers, then my complex numbers come for my roots will come in pairs. They'll come in even pairs. So already we can see some things. If I look at some random polynomial, we can figure out what its degree is, and we know it has this many factors. We know that those factors are going to be the zeros, and those zeros come from maybe complex numbers. Remember, real numbers are part of the complex numbers, so it comes from some kind of complex number. And in particular, if I have coefficients that are all real, then I happen to know that my roots, if they do involve honest-to-goodness complex-only numbers, then they're going to come in pairs. So now we wrap it off with the two slightly more useful pieces of what we're talking about. Descartes' rule of signs says that provided my polynomial has real coefficients, so just like up here we asked it to have real coefficients, then the number of positive roots, so now we're getting into the specifics. What are these roots that are living maybe inside the complex number field? Well, they're going to be positive or negative or complex. They're complex, we know they're going to come in pairs if they have real coefficients, but the positive ones is either going to be equal to the number of variations in the sign of our polynomial. So what does that mean? That means when we look at our polynomial coefficients, we're going to look at how many times the sign changes. And either the number of positive roots is going to be the same as that number of signs, or it's going to be less than that by an even number. Things come in pairs. If you've got real coefficients, then your complex numbers come in pairs. If you've got real coefficients, then your positive numbers are going to come in either the same as the number of variations in the sign, or less than that by an even number, so they're going to go away by pairs. Same deal, if we plug in -1 into all of our x's, that'll switch all of our odd exponents, signs, and then we can count up how many times the sign varies in that. and that will tell me how many negative roots I have. I think it's very easy right now to think, oh, Descartes' rule of signs might be kind of complicated. It's not actually all that complicated when you see someone do it, which we'll do in a second. It's just tricky when you think that you have to sort of read through this and figure out what it's saying. So we'll use Descartes' rule of signs in a second. We also, though, first want to talk about upper and lower bound. If we do our synthetic division, we have our coefficients all written up, and we do our synthetic division process and figure out what we've got, then if in that low row at the bottom, if that low row, if every term is non-negative, then we know that the number we tried to divide by, it wasn't a root, maybe, because it didn't give us 0 in that last spot, so it might not be a root, but it will be what we call an upper bound. That positive number we were dividing by, we thought it might be a root, it wasn't, but it is an upper bound. So we don't have to look higher than that for more roots. We know that our roots have to be smaller than this number if we get all those positives. And the flip side of this is that if you try dividing by a negative number, we'll call that D instead of C, but if we're trying to divide in our synthetic division by a negative number up here, and if when we do that, in the bottom row, each of the terms alternates sign, and if you get a 0, that's okay. It can be either positive or negative, whatever you want it to be to try to make that alternating pattern happen. Then we found ourselves a lower bound, so we don't have to look lower than that number. So what I want to do is take a look at a polynomial that's too big for a calculator to handle, and we're going to figure out how many linear factors it has. We're going to figure out that means we have so many roots. We're going to figure out how many possible complex numbers we might have in pairs, provided we've got these real coefficients. Using Descartes' rule of signs, we're going to figure out all the possible combinations of positive roots and negative roots. And also then we're going to take, and I'm just going to pull 4 numbers out of thin air, and we're going to try to divide by those and see if we can maybe figure out some upper and lower bounds. If you think back to the previous video that we did in this series, we're still not quite sure how to find roots, but we are getting close, particularly this upper bound and this Descartes' rule of signs. These start to tell us how many roots we're expecting and whether they're bigger or smaller than certain numbers. All right, so I've got my little answer box there nicely typed out so you can read my handwriting, but let's look at P of x equals x to the 7th plus 21x to the 6th minus 10x to the 5th minus 528x to the 4th plus 1,367x cubed negative 13089x squared plus 1,378x minus 840. And let's run through these facts with it all. So we know there is a root because that's what the fundamental theorem of algebra tells us. We also know by the factorization theorem that since we've got the degree of my polynomial 7, that I'm really talking about having 7 roots. So there are 7 roots total. That might include multiplicity, and that's this column over here. However many my positive, negative, or complex roots, they all better sum up to 7. All right, so much for fundamental theorem of calculus and factor theorem. Each of these does have a positive, not a positive, but it has a real coefficient. I have no imaginary numbers with any pieces, no square roots and negative ones. So this means that if I am going to have complex numbers and I have one, I'm going to have the other as well. So you'll notice my complex numbers are always going to come in nice even numbers because I'm going to have those nice even number pairs. Descartes' rule of signs. It says this: the number of positive roots is going to either be equal to the number of variations in sign or less than that by an even number. So let's count up our sign variations. This is a positive number, this is a positive number, this is a negative, so I have one variation. It stays negative, negative. It's positive, I have another variation. Now it switches to negative, it varied again. Now it switches to positive, it varied again, it switches again. So I have 1, 2, 3, 4, 5 different times my sign changes. So I might have 5 positive roots, but it says in Descartes' rule, either equal to this number or less by an even number. They go away in pairs. So I could have 5 positive roots, or 5 minus 2 gives me 3, or 3 minus 2 gives me 1. It doesn't make sense to subtract 2 from 1. I'd have -1. You can't have -1 as something you can count. So I'm guaranteed at least one positive root. I might have 3 or 5. Next, Descartes says this: if we plug in a negative number and change all of our signs that have odd exponent, then we're going to have a different set of variations. So let's look at what that would look like. Let me do that just nice and quick here, and maybe we can use a different color. So if I plug in p of negative x, what am I going to get? Well, I'm going to get negative x to the 7th, still plus 21x to the 6th, because 6 is going to make that negative go away. Plus 10x to the 5th, still minus 528x to the 4th. Minus 1367x cubed, still minus 1389x squared. Minus 1378x, and of course still minus 840 because I can't plug a negative x into there. So now if we count them up, I've got a minus sign changes to a plus. Here's one variation, still pluses, it's changed to a minus. Here's another variation. It stays minus all the way throughout. So there's only 2 variations. This means for my negative roots, I'm either going to have 2 or less than that by an even number, so I might have 0. Because I can have different combinations, you'll see that these 2 columns here don't decrease as nicely as the positive root 1 did. That's just because I chose to make that positive root 1 show up there first. So now we can work it out. If I have 5 positive roots, since I have 7 total, that leaves me with 2 to play with. I could either have 2 negative roots, in which case I'd have no complex roots because 5 plus 2 gives me 7 and there's no roots left. Or I could have no negative roots, because that's 2 less than 2, in which case then I'd have to make up the 2 more roots to add up to 7 in a complex number. On the other hand, if I only have 3 real roots, I've got 4 roots left to make up that 7. So either I could put 2 of them in each, or I could put all 2 in the complex numbers, because that will come up into 4. And finally, if I have 1 real root, well, what could I have? I could have 2 negative roots, and in which case I could have 4 complex roots, or I could have 0 negative roots, in which case I have to make up all 6 here. The only possibility for my negative roots is 0 or 2, so I don't have a lot of playing room there. If I only have 1 real root that's positive, I don't know not much about whether my negative roots are going to be 0 or 2 still, but I do know that I'm guaranteed at least 4 complex roots. So now we know a little bit about how this guy's going to work. We know what's going to happen here. This is the kind of chart you imagine filling in. And once you know this, we're almost good, except we can do a little bit better than simply knowing what sort of pattern we're going to have. This is mostly helpful for error checking. If someone walks up to you and says, look, I factored p of x, and in fact it has 16 roots, you're going to say you lie. That doesn't make any sense. If, on the other hand, I'm factoring something, I say, look, I've got 5 positive roots, and I've got 1 negative root, and I've got 1 complex root. That equals 7. You still know they're lying. So now let's use the upper and lower bound. And let's try it with just some random numbers that I'm going to pick. I'm going to pick negative 30, negative 10, 2, and maybe 5. And these all together should let us figure out maybe where some of the bounds are. I'm only picking a number as small as negative 30 because I'm seeing some large negative numbers here, and it seems like maybe something should happen. Based on the pattern, and that's kind of key. We don't care about what's really happening with the numbers so much. We more care about the pattern of the synthetic division. So let's take a look at this. Well, with synthetic division, I'm going to have 1, 21, negative 10, negative 528, positive, I guess I don't really need to write the positive, 1, 3, 6, 7, negative 1389, 1378, and negative 840. Let's try negative 30 first. Now here's the deal. Since I'm trying to divide by something that was a negative number, we're talking about the second piece of upper and lower bound, and if I have alternating signs, then we're going to know that negative 30 is in fact a lower bound. So let's try it out. Carry the 1 down, and negative 30 times 1 is going to give me negative 30. Negative 30, and that's going to give me 9. 9 times negative 30 is going to give me negative 0, 270. It's going to be positive because of the negatives. What we're going to notice here is a very interesting pattern. If I add these up, I'm going to have 260. If I multiply 260 by a negative number, I'm going to get a large negative number. But right here, 260 times negative 30 is going to be a very large negative number. When I combine these two together, I'm going to get a very large negative number. Negative times negative is going to give me positive. It's going to be very huge and positive. These are going to give me a positive number overall. Positive times negative gives me negative. The point is I have no hope of getting a 0 over here, because these numbers are ending up being negatives and positives and negatives. And so instead I'm going to get a very large negative number. Maybe in the millions probably, because negative 30 is pretty big, and I'm multiplying some pretty large numbers by negative 30. All I care about is that I have positive, minus, positive, minus, positive, minus, positive, minus. This is that alternating sign that we're talking about. And that means that we're looking at negative 30 as being a lower bound. We don't know what the root is. No idea what the roots are. But they're in between negative 30 and some larger positive number. All right. And the thing is here too, notice, we didn't care about what the actual values of these numbers were. In fact, I'm very much not inclined to try multiplying them out, because that would be a lot of work. Instead, it was pretty quick to figure out how the signs went. And that was all we really cared about. So now we can keep on going. We could try negative 10. Same thing, 1, 21, negative 10, negative 528, 1367, negative 1389, 1378, negative 840. Now we're trying it with negative 10. Same idea. If I get alternating signs, then I know I don't need negative 30 as my lower bound. I could go in here and replace it with something better as a lower bound, negative 10. You like your lower bounds to be as small as possible. It tells you where to look. I pull the 1 down, get myself negative 10. That leaves me with 11. And as soon as I get that, I stop. Why do I not even do here? Look. These are both positive numbers. I don't have alternating signs. The lower bound theorem says that if I'm dividing by a negative number, I need to have alternating signs for anything useful to come out of this. So as soon as I don't get alternating signs, I stop. I might try it just a little bit further. And somewhere here, realize that because I'm going to add these up together, and I'm going to get myself, what, 672? This is such a large number, by the time I multiply it out, again, I see that there's no hope of this secretly being a root. It's certainly, because these are both positives, not going to be a lower bound. So I don't even care about this number. It doesn't do anything for me. All right. So, carrying on, 1, 21, negative 10, negative 528, 1367, 1389, 1378, negative 840. And now let's try the next number I picked, which I think I picked the number 2. So I pull a 1 down, and then I get myself 2, and then I get myself 23. Keep in mind, what are we looking for here? To be an upper bound, if we're doing a positive potential root number, then we're looking for all of our terms to be non-negative. So we're looking for positive numbers and zeros. So far it's going good. 23 times 2 is going to give me 46. 46 minus 10 is going to give me 36. 36 times 2 is 72. Subtract 528 from that, and then make it negative 456. 456 times 2 will give me negative 912. Subtract that from 1367, and we'll get 455. Multiply that by 2, and get ourselves 910. Subtract 1,389 from 910, and that will give us negative 479. Multiply that by 2, and I should be getting negative 958, which should give me 420. Multiply 420 times 2, that's going to give me a positive 840, and that gives me 0. I kept on going, even though as soon as I got this negative, I was a little bit worried because it wasn't going to be an upper bound, but I kept on going because I noticed that my signs were kind of alternating now, and they kept on being pretty decent numbers that were pretty close to the 840 I needed. So what I'm saying here is that even though it's not going to be an upper bound, I had hope of a 0. And that hope paid off. I got a 0 there. This means that this guy factors. I didn't find an upper bound, I found something even better. I found an actual 0. Then I have what? Now it's next to the 6, plus the 23, x to the 5th, plus 36, x to the 4th, minus 456, x cubed, plus 455, x squared, minus 479x, plus 420. And I think my last number that I was interested in checking out was positive 5. And if I'm trying to find upper bounds, rather than do synthetic division on my original piece here with 5, I might as well do it on the coefficients of this smaller piece. Since they're factors, they should have the same upper bounds. And since I was so lucky as to find an actual root, I shouldn't let that opportunity go to waste. I have much smaller numbers this time to perform synthetic division on. This is being efficient, and this is a big part of math. Understanding not just the answer you were wanting, because here we were kind of maybe hoping that 2 would be an upper bound, and I'd have all sorts of positive numbers here that were non-negative. But don't just grab the numbers that you're interested in and find answers that you want. Look for actual answers even out of perhaps things you weren't expecting. If you understand what's going on, it makes the whole process a lot more efficient. So now I'm going to finally try 5 and see if that works. I pull the 1 down there. 5 times 1 gives me 5. Add those together. That gives me 28. 28 times 5 gives me 56. 56 plus 36 should give me 92. 92 times 5 is going to give me 460. Add those together. That should leave me with positive 4. 5 times 4 is 20. And 20 plus 455 is going to give me 475. And right about here is when I stop. If I multiply 475 by 5, I am going to get 2,375. The point is this is going to be a positive number, and a positive times a positive is going to give me a positive, and adding 2 positives together leaves me with a positive. There's no hope of this being root. Rather depressing to keep on writing no hope here. But the main point is it's not a 0, but it is also an upper bound. So what have I learned? Well, I've learned that negative 30 is a lower bound for all of my roots. I've learned that 5 is an upper bound. And also, we've learned that 2 is a 0. That's just from picking 4 random numbers and playing around with this. We can keep on going, but we don't need to. We've got better ways of figuring things out. So what have we done? Well, we figured out how many roots something's going to have based on the degree. We figured out that complex numbers, as long as our coefficients are real numbers, are going to come in pairs. Thanks to Descartes' rule of signs, I got positive 2 as a root, so I know that I have at least one positive root. I found it. His name's net positive 2. I don't know yet which one of these rows is the correct pattern yet. We have to keep on working. But I do know that if I'm looking for more of my numbers, I'm going to be looking inside negative 30 to 5 on the number line. So instead of looking at any number anywhere in the world, I could look for some. And I even learned that even though negative 30 is kind of a pretty small negative number, negative 10 wasn't small enough. It didn't have that alternating pattern going on there. I might next try negative 20, try to whittle down this lower bound and crunch it in closer. So instead of talking about the negative number line from negative 30 to 5, maybe negative 20 to 5 will be just as good, and I can cut out 10 whole numbers that I might be having to think about. And of course, there's not just 10 whole numbers in there, or I guess natural numbers, there's all sorts of fractions in there as well. So this is really saving me a lot of work if I could cut this piece off by next trying negative 20. So I think that's where I'm going to leave this. Go back, remember we have the new shorter piece here that we've got since it's factored, so go back into here and try to factor this guy out yourself using negative 20. And see just what you might get.